Bagaimana?
Punten Pak Sukma sudah bisa mengaktifkan videonya?
Ini pidatonya nih.
Pak Sukma, mohon dihidupkan videonya.
Sebentar ya. Kenapa jadi hilang? Bisa mendengar suara saya?
Bisa Pak.
Ya.
Tinggal videonya saja Pak. Kameranya diaktifkan.
Bentar. Ini ya. Ini. Udah sekarang. 2 kali. Ini Zoom.
Ya.
Oke. Mati lagi Pak Sukma.
Ada ya?
Ya, mati
Barusan
lagi.
ada.
Barusan sudah muncul.
Ini lagi dah. Asistennya nih. Nggak keluar. Video. Sudah ya, ada ya.
Ya, sudah. Okay, ladies and gentlemen, before the dissertation defense is started, please set up your mobile phone into silent mode. And it is not allowed for all of you and also all attendants to share any material during the promovendus giving presentations. And because it will disturb its process. Okay, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Greeting for all of us, especially all attendants who join this dissertation defense through YouTube channel. With Bismillahirrahmanirrahim, I declare that this dissertation defense is started. This dissertation defense is held to give opportunity to promovendus Mr. Tarwadi to deliver his dissertation research with title of synthesis, characterization, and in vitro evaluation of lipopeptides and oligopeptides-based liposomes for gene delivery vehicle candidates. And answer question or defense his dissertation against critics common in this session. Promovendus has been doing his dissertation research under supervision of a team promoters as follows. Professor Dr. Sukma Jaya Asari from ITB as Chief of Promoter. Professor Dr. Heni Rahmawati from ITB as Chief Co-Promoter, Dr. Rahmana Imran Kartasasmita from ITB as co-promoters. While the examiners in these sessions are Dr. Tri Suciati from ITB, Dr. Ratna Anisa Utami from ITB, Dr. Rosaihu Rizal El Mutakin from the Centers of Pharmaceutical Technology and Medical Device, BPPT Indonesia. Ladies and gentlemen, next I will ask the Chief Promoter, Professor Sukma Jaya Asari, to deliver curriculum vitae of promoter vendors, and then to convey academics accountability regarding to the acceptance of this dissertation. Please, Professor Sukma. Professor Sukma, do you hear our voice? Professor Sukma, do you hear our voice from here?
Saya telepon ya Pak ya.
Okay, please.
Sorry, Bapak-Bapak, Ibu.
Okay, Professor Sukma, please please deliver curriculum vitae of vendors, and then please convey academic accountability regarding to the acceptance of this dissertation. Silakan menyampaikan CV promo vendors dan pertanggungjawaban akademik.
Bentar ini gambar. Nggak keluar.
Yeah, it is okay, Pak Sukma. Okay, okay. We can see you.
Mau cari teksnya ini. Wah, udah. Sorry ini. Jangan jalan-jalan. Sorry, sudah. Ada.
Okay,
Ya.
please.
Ibu. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Hadirin yang saya hormati, Saudara Tarwadi ini tercatat lahir tanggal 15 Juni di Jawa Tengah, yaitu di kota Pemalang. Lulus sarjana S1 di Farmasi ITB tahun 94. Lulus S2-nya dari program sandwich antara BPPT dengan Australia. Saudara Tarwadi ini merupakan staf pusat teknologi farmasi dan medika, saya kira di BPPT, dan pada tahun 2016 pada semester genap tercatat sebagai mahasiswa S3 di ITB. Kemudian penelitian yang dia lakukan adalah berinti pengantaran material genetik menggunakan vektor sintetik. Pada disertasinya, Saudara Tarwadi ini mendesain dan mensintesis agen yaitu transfeksi berbasis peptida, yaitu lipopeptida dan oligopeptida. Pada tahap awal, lipopeptida yang mempunyai rantai pendek yang tersusun dari asam amino sistein, histidin, lisin, dan rantai alifatik dari asam laurat dan asam palmitat. Rantai samping alifatik itu dari laurat dan dari palmitat dimaksudkan untuk menginisiasi interaksi antara molekul DNA dengan lipopeptida. Sedangkan asam amino sistein dimaksudkan agar senyawa lipopeptida membentuk senyawa dimer saat berinteraksi dengan molekul DNA, sehingga terbentuk partikel kompleks DNA lipopeptida dalam ukuran nanometer. Histidin berperan agar lipopeptida melindungi molekul DNA dari degradasi enzimatik. Hasil uji in vitro, senyawa lipopeptida rantai pendek dapat membentuk kompleks dan melindungi DNA dari degradasi enzimatik. Bertambahnya molekul histidin dalam senyawa lipopeptida menjadikan kompleks DNA dengan lipopeptida menjadi lebih besar. Sementara bertambahnya lisin menjadikan ukuran partikel kompleks menjadi lebih kecil, bahkan sampai bernilai 200 kali. Dan akan meningkatkan efisiensi transfeksi pada sel mamalia. Pada hasil uji in silico, terdapat senyawa lipopeptida rantai pendek dan menunjukkan senyawa ini dapat berikatan dengan senyawa reseptor protein importin alfa yang memfasilitasi terjadinya transport aktif menuju inti sel. Untuk meningkatkan efektivitas ikatan antara molekul DNA dengan agen transfeksi, disintesislah senyawa lipopeptida dan oligopeptida yang mengandung sekuens TAT dan NLS yang dapat meningkatkan penetrasi lipopeptida pada membran sel. Dan inti sel. Hasil uji karakterisasi fisikokimia menunjukkan bahwa DNA dengan lipopeptida mengandung sekuen TAT dan NLS, dan DNA dengan oligopeptida mempunyai ukuran nanometer yang lebih kecil. Demikian yang dapat saya sampaikan. Terima kasih atas perhatian.
Thank you, Professor Sukma. Now, could you please invite promovendus to attend this sessions, please?
There.
Hello, Mr. Tarwadi, do you hear our voice here?
Yes, okay.
Okay. Promovendus, are you healthy enough to perform this dissertation defense?
Yes, sure. Thanks.
Okay. You are given opportunity to present your dissertation research in maximum 20 minutes. Time yours, please.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Bapak pimpinan sidang dan Bapak Ibu yang saya hormati, selamat sore. Izinkan saya dalam kesempatan ini menyampaikan presentasi ini dalam bahasa Inggris. Good afternoon everyone and good evening to Dr. Jalal Jazari in Melbourne. Thank you very much for this great opportunity for me. My PhD research is dealing with gene delivery entitled Synthesis, Characterization, and in vitro evaluation of lipopeptide and oligopeptide-based liposome for gene delivery vehicle candidates. My supervisors are Professor Sukma Jaya Ashari, Professor Henry Rahmawati, and Dr. Rahmana Emran Kata Sasmita. In principle, gene therapy means you deliver gene interest to cure the disease. It can be carried out by direct delivery or ex vivo treatment, where you take out the cell from the patient and modify the cell in the lab before returning it to the patient. The problems with gene delivery is how to deliver the gene safely and efficiently. Currently, at least 20 gene therapy products commercially available. This is to give us some perspective on gene transport inside the cells. There are several gene transfer barriers that have to be resolved. Firstly, DNA binding. DNA has to transfection agent efficiently. Secondly, cell uptake. DNA has to be internalized into target cell. Thirdly, DNA endosomal escape. The complex of the DNA has to escape the endosome before the degradation process in the lysosome. Then DNA has to enter the cell nucleus. When inside the cell nucleus, the DNA has to be released from the complex before the gene expression is achieved. Therefore, an ideal transfection agent has to be bind to, protect to, and compact the DNA effectively. It should be non-cytotoxic, mediate endosomal escape, and facilitates transgene expression. Why do we focus on peptide-based transfection agent? Ladies and gentlemen, since 2003, there were several publications of lipopeptide and TAT analysis as transfection agent. Recently, in 2018, it was reported that oligohistidine enhanced the transfection of TAT analysis peptide. Still, we need important information regarding the relationship between the transfection agent structures and transfection efficiency. In regard to TAT analysis peptide, we assume this peptide might bind tightly to DNA and resulted in low transfection efficiency. Therefore, two main things we did in this research. Firstly, seeking the relationship between the transfection agent structure with transfection efficiency. And secondly, developing a new transfection agent which is safe and effective. Ladies and gentlemen, the scope of this research was to design and synthesize transfection agent, carry out complex characterization, cytotoxic study, and performing in vitro transfection evaluation. The objective of this research was to develop a safe and efficient lipopeptide and liposome-based transfection agent. The objectives were emphasized on the synthesis and complex characterization, cytotoxic study evaluation of transgene expression, and preparing peptide-based liposome to enhance transfection efficiency. There were three stages of this research. Firstly, the synthesis of the transfection agent and complex characterization. Secondly, the transfection process and the liposome preparation. And the third stage regarding cytotoxicity study and liposome evaluation. Ladies and gentlemen, we got four major findings as the novelty of this research. The relationship between lipopeptide structure and transfection efficiency was achieved. Palmitil with cysteine, lysine, and histidine, or we call it lipo-1, facilitate more luciferase transgene expression than the control polylysine and comparable to polyethyleneamine. Secondly, lipopeptide transfection was modulated by chloroquine and bavillomycin. Polyethyleneamine co-transfection and lipopeptide-based liposome enhance the lipopeptide transfection efficiency. Then the third one, lipopeptide composed TAT analysis facilitates more GFP expression compared to the shorter lipopeptide and polylysine. And the fourth one, oligopeptide-based liposome has low cytotoxicity from homogeneous complex and facilitates GFP expression comparable to the control lipofectamine. Dear ladies and gentlemen, let us have a look at the result in more detail. First, I will focus on the short lipopeptide as transfection agent. Here we are. We have designed the short lipopeptide composed of an alkyl chain and amino acid. Alkyl chain was included to initiate hydrophobic interaction. Meanwhile, a short amino acid sequence was included to condense and mediate DNA escape from the endosome. We ordered the short lipopeptide from Auspep Corporation, which is in Victoria, and the LCMS spectra confirmed the molecular identities of the short linear lipopeptide. We have characterized the complex of lipopeptide DNA. Firstly, we did ethodium bromide exclusion assay. Here, the lipopeptide condensed DNA effectively. But when the reducing agent such as tritiotritol or TTT was present, the lipopeptide couldn't bind to DNA effectively. Secondly, the data on agar-stress electrophoresis assay revealed that DNA was retained in the well. In the presence of DNAs, the DNA molecule were protected by the lipopeptide, as the DNA band wasn't observed in agar gel. Then we evaluate the complex particle using Malvern nanosizer. This is the result. As the charge ratio increased, the particle size of the complex decreased. The inclusion more lysine in the lipopeptide decreased the peptide size, and vice versa for the histidine addition. Then we evaluate the luciferase transistor expression after we do optimization. Here we are. Ladies and gentlemen, amongst the short lipopeptide, palmitil with 1 cysteine, 2 lysine, and 2 histidine, or we call it lipo1, facilitates more gene expression than others. Its transfection efficiency was comparable to the control polyethylenediamine. There was a relationship between the lipopeptide structure and the transfection efficiency. We also carry out in silico studies, although this is only the small portion, and found that this lipopeptide might involve in the nuclear uptake process. Ladies and gentlemen, the transfection efficiency actually needs to be enhanced. And here we are. The transfection of chloroquine and perfilomycin modulated the lipopeptide mediated transfection, as we could see in the graph. The gene expression can be further enhanced by transfecting the cell with the lipopeptide-based liposome or by co-transfection with polyethylenediamine. Dear ladies and gentlemen, now we're focusing on the second result, transfection agent that is based on the TAT analysis sequence. We have designed the transfection agent, which actually based on the short lipopeptide sequence that we already done. TAT analysis sequence were included in the lipopeptide structure to enhance cell membrane penetration, and this synthesis was carried out using an automatic peptide synthesizer. We synthesized oligopeptide and lipopeptide, which composed of 17 and 23 amino acids. Now, the important question, does the transfection agent condense DNA more effectively than the shorter lipopeptide? And the answer is yes, it does. This is the result. The particle size of the shorter lipopeptide changed over the time incubation. In contrast, the particle size of the transfection agent based on TAT analyzed peptide almost unchanged for 20 days observation. It seems for us that the number of charges on the transfection agent affected the complex stability. And now we would like to use stem image analysis to confirm the particle size. Let us have a look at this result. TEM data confirm that the complex of DNA with the short lipopeptide or lipo1 tend to aggregate. Meanwhile, the complex of DNA with the transfection agent based on TAT analysis, whether oligopeptide or lipopeptide, was homogeneous. Our particle complex was comparable to the complex of polylysine DNA and polyethylenediamine DNA as reported by others. Now, let's have a look at the cytotoxicity assay. The transfection agent was less toxic than the control in here compared to polylysine. But however, the cytotoxic study revealed that the charge, the positive charge of TAT NRS reduced cell viability. Now we would like to move on transfection studies. Here we are. The transfection studies on CHOK1 cell displayed that the lipopeptide with TAT-NLS or lipo2 facilitate more GFP than polylysin and also more GFP compared to the short lipopeptide or lipo1. But unfortunately, GFP expression facilitated by oligopeptide was much lower than those by lipo2. Dear ladies and gentlemen, now we're thinking about liposome. So far, we had found that the complex of transfection agent based on TAT-NLS DNA stable and in compacted size. However, the gene expression was only moderate or even very low. Why? We thought that DNA was bound to oligopeptide, in here mean TAT-NLS, very tightly. Then we formulate liposome to loosen the tight ionic interaction between the oligopeptide and DNA. Ladies and gentlemen, we characterize the complex before further performing in vitro evaluation. Data on DNA mobility shift acid displayed that liposome retain DNA in the well of agar gel. Next, we would like to evaluate the liposome DNA stability since liposome stability often the problem. Here the data. Compared to others, the lipopeptide-based liposome was the most stable, with a complex size of about 200 nanometer. It was interesting to note, as expected, that the presence of polysorbate or 2020 reduced the complex size significantly. We also found a similar result to Huang et al., where the complex tend to increase its particle size after a couple of weeks. We also confirmed that the liposome DNA complex size using the TAM apparatus. This is the result. TAM image of liposome and liposome DNA complex, as we can see in the slide, that the liposome particle size was smaller when first it condensed DNA, secondly an increased oligopeptide concentration in the liposome formula, and thirdly the addition of twin 20 in the liposome. In the presence of this twin, the particle size decreased significantly to only 50 or up to 100 nanometer. Let's move on to other data regarding cytotoxicity. Here we are. Cytotoxic study on HEG2 cell revealed that oligopeptide was less toxic than the commercial product. In here, we compare to polylysin and lipofectamine. Dope was non-toxic to the cells. However, the presence of twin 20 in the liposome clearly reduced the cell viability. Now, we are coming to the most crucial question. Does the liposome increase GFP transgene expression as expected? And the answer is yes, it does. We found fascinating data here. The liposome obviously facilitates more GFP expression than oligopeptide itself. Clearly observed here that GFP expression mediated by the liposome was comparable to lipofectamine. However, the presence of twin 20 in the liposome reduced GFP expression significantly. Ladies and gentlemen, this is the last data I share at this moment. And now we will focus on the conclusion. Firstly, peptide-based transfection agents are efficiently designed and synthesized, and the relationship between short lipopeptide structure and transfection efficiently was achieved. Secondly, the lipopeptide mediated transfection was modulated by chloroquine and bapillomycin, and this transfection was enhanced by at the lipopeptide-based liposome and polyethylamine co-transfection. Thirdly, the lipopeptide composite analysis sequence, in here mean lipo2, form a stable and homogeneous particle with DNA with particle size 120 nanometer, mediate more GFP expression than polylysine and the short lipopeptide. And this is the most important one. Oligopeptide-based liposome was relatively non-cytotoxic and facilitates GFP expression comparable to the lipofectamine 2000. Twin 20 in the liposome formula reduce the complex size, but it also reduces gene expression significantly. And next, this is the future work. Firstly, we suggest to do a lipopeptide structure optimization. Secondly, liposome formulation, which have to be stable and non-toxic and capable to facilitate transgene expression on non-dividing cells. The third, nuclear uptake studies. This is to understand the molecular mechanism of gene delivery vehicle by peptide-based transfection agent. And number 4, toxicity and efficacy studies with gene interest on animal models. We have a publication in national journal as well as international journal. Amongst international journal manuscript, we have 2 manuscripts still waiting from the decision, but we already published 3 journal in international journal. This is the international seminar that we participated. And finally, I would like to thank my co-supervisor sincerely, Professor Sukmajaya Ashari, Professor Heni Rahmawati, and Dr. Rahmana Embankata Sasmita for the guidance, valuable feedbacks, and tremendous support during my research in ITB. Special thanks also go to Professor Colin and Dr. Jalal Zazayari as my previous supervisor in Monash University, Parkville campus, who introduced me research on gene delivery and join this important session. We would like to thank several institutions which support my research: ITB, BPPT, ISTECTT, Melbourne University, where I synthesized the peptide, Monash University, Parkville campus, Australian Development Scholarship, Nanocenter ITB, and Biopharma, where I characterize the complex. And finally, my beloved family, Dewi, my lovely wife, and all the fantastic kids, Taki, Tia, Alfa, Ahmad, and Ade. Sure, without their affection, love, and support, I couldn't carry out this PhD research. Again, thank you very much to all colleges, to all school pharmacy staff, to all people and all institutions, which I couldn't mention one by one, in helping and supporting me during my PhD candidature. My God Almighty rewards you with the best rewards. Amin ya Rabbal Alamin. Sekian, terima kasih, hatur nuhun. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Promovendus, for your nice presentations. Ladies and gentlemen, this session is continued with questions and comments. After all examiners and promoters giving comment or questions, I would like to invite Dr. Jalal Zazazeri to give or deliver comments or questions. Okay, first I would like to ask external examiners, Dr. Saihur Rizal El Mutakin, first to deliver some question or comment, please.
Thank you very much for that. I know Tarwadi, I mean, since going back many years now, since he was doing some study with us at Monash University, and he has been doing a fantastic job, and we have published a few papers together. And I really enjoyed your talk today, Tarwadi. You have done a great amount of work, and you have continued what you had started in Monash quite well And I see that you have a number of international publications. In fact, one accepted only last week. So I congratulate you on that. And I'm quite impressed with how much you could manage to do since you have kind of left us. That I thought it's all finished when you left us, but we just started with all of that. And I have no question at this stage, and I really enjoyed your talk. Well done.
Thanks a lot, Jalal. Thanks a lot.
Thank you, Dr. Jalal. Okay, I would
Thank
like
you.
to invite Dr. Sahrul Rizal El Mutakin to deliver some question or comment.
Okay, thank you, Prof. Tarwadi. Thank you very much, thank you very much, Prof. Daryono, for the opportunity, and also thank you very much for Pak Tarwadi for the nice presentation. So I want to ask, I have one question. Could you show me the slide number 12, please, Pak Tarwadi?
Yes, sure. Yeah.
Yes, that slide. So this is a very important data, I think. But I just want to make a relationship between each data that I read in your dissertation. First, I want you to focus on the 5 bar from PLL, and then and from PLL until LiPo1.
Yeah.
So this 1, 2, 3, 4, 5.
Yeah.
PLL until LiPo1, and also polyethylene-imine.
Yeah.
So the 6 bar here. So I just want to ask you the relationship between the transfection efficiency here and with the other parameter. The first one is if we see the data of the particle size, PLL low, say, and then the next 4 bar PLL, and then the next 4 bar, their particle size is similar, and also including the PI. However, the transfection efficiency quite different. So that's my finding from your dissertation. So next you can explain more detail about the relationship between the transfection efficiency and also the particle size. The another parameter that I want to compare is the condensation capacity. If we see on your dissertation data regarding the condensation capacity, only PLL and also polyethylene-imine, which have quite effective condensation capacity. The others was not that much. However, again, between PLL and polyethylene-imine, the transfection capacity was quite different. PLL was quite low, but the PI is very superior. And then the last thing that I want to also compare is zeta potential. PLL and polyethylene-imine do have a very high zeta potential, relatively high zeta potential is quite high, I think 12 and 15. But the other 4, low CK2 and until LiPo1, the zeta potential was, I think, 4 times lower than the polyethylene-imine and polylysine. But again, the particles, the efficiency was not that very different. So it's quite difficult to make a conclusion from this relationship. Could you explain or elaborate more detail for us? Thank you, Pak Tarwadi. That's my question.
Okay, please, Mr. Tarwadi.
Okay, thank you, Dr. Saiful Rizal. Firstly, I'll be focused on the particle size, and then condensation capacity, and then the third one is zeta potential. As we can see here, that the transfection efficiency compared to others, palmitil with 1 cysteine, 2 lysine, and 2 histidine, or we call it LiPo1, is the best among others. But yes, not really significant. When we compare to polylysine, yes, it is very high. But when we compare to lipofectamine, yeah, it's still very low. In here, because we only measure the particle size and also the condensation assay, we assume or we speculate that this is because even though, as you mentioned, that the particle size is not so different, But among others, lipopeptide 1 or lipo1 is relatively smaller compared to palmitil with 1 lysine and the one with lauryl, because as we can see in the particle size data on the condensation data, even though it is not very significant, the difference between them, palmitil with 1 cysteine, 2 lysine, and 2 histidine is relatively smaller in particle size, as well as effective in condensing DNA. So we speculate that because of the particle size and as well as the condensation ability, lipo1 or the palmitil CKKHH is more effective in mediating gene transfer. Secondly, a condensation capacity regarding polylysine and polyectamine. Yes, polylysine was very, very efficient in condensing DNA. We found it, and in every publication, we found it like that. Even when we see the TEM image analysis, the particle size of the polylysine DNA was very, very low. I mean, very small, about 100 or 120 or something like that. But the mediation in gene expression, polylysine is very, very low. Here, some publication mention that even though polylysine very effective in condensing DNA, but it couldn't, the polylysine couldn't protect DNA from DNA during the transport inside the cell. And that's why the mediation by polylysine is very, very low compared to polyethylenamine. Meanwhile, polyethylenamine, as many researchers cite, that it involved in proton response mechanism to fuse with endosome and then release the DNA from the endosome. And some other publications said that polyethylenamine also protect the DNA and enter the nucleus. In some publications say like that. So that's why, even though the capacity in condensing DNA, polylysine is equal or even better than polyethylenamine, but the mediation of the gene is very low compared to polyethylenamine and also to other transfection agents that we design. And the third, regarding zeta potential of polylysine and polyethylenamine. Zeta potential is actually confirming the potential between the particle in dynamic light scattering measurement. And it tells us in practically, if the value of the zeta potential is pretty low, telling us that the complex tend to aggregate. Meanwhile, if the the zeta potential value is pretty high, say above 15 or above 20, telling us that the complex are relatively stable. And this is this is important for the cell uptake as well as the transport of the complex inside the cell. So that means if we would like the cell uptake effectively, the particle size, the zeta potential have to be positive because the cell membrane is negative. So that they have to get interaction. But if it is too high, we speculate if the particle size, the zeta potential is too high, even though the particle is stable, probably it might harm to the cell. So that's why in transfection agent, the zeta potential value has to be adjusted in certain numbers, not too high, but not too low, in order not to be aggregate. That's what's my understanding, Dr. Isaac. Thanks a lot, Prof. Dayono.
Okay, thank you, Mr. Tarwadi. And next, please, Dr. Ratna Anissa Utami for times to give a question or comment.
Okay, thank you, Professor Daryono. Congratulations for Promovendus, Mr. Tarwadi. Thank you for your nice presentation. However, I have two questions. First question, in your research, you develop agent or system for the gene delivery into the nucleus, and we know ideally factors for the gene delivery have several characteristics. First, such as capable of condensing plasmid DNA into small particle size, resistant to the nucleus degradation, can escape from the endosome, yeah, be non-toxic and non-immunogenic, and etc. Yeah. My question is whether your research results have been fulfilled the ideal characteristic according to the existing theory, because surprisingly, for example, the lipofectamine, yeah, actually have a higher particle size, more than 200 nanometer, but it has higher efficiency.
Yeah.
And then, do you find something different between your results compared to the existing theory, and how do you explain about that? My next question, second question, in your presentation, you state that oligopeptide based on liposome in your study have a similar advantage to lipopectamine, which is the lipopectamine is the standard goal for the transfection agent. And do you think your research data is strong enough in terms of quantity and quality to sustain that the conclusion that you have drawn? Okay, thank you.
Okay, thank you so much, Dr. Ratna. So first, I'll focus on your first question regarding the ideal transfection agent. As I mentioned before, that ideally the transfection agent has capability to condense, to make a particle size small enough, mediate endosome escape, and also mediate nuclear uptake. And we found a very interesting data here actually. When we see the complex of oligopeptide DNA is really not toxic, and then a compact size, condensed very good, but then the expression is very, very low. And we thought that DNA actually have very strong interaction with oligopeptide, and once they escape from endosome, because we try to include the histidine, actually it's very difficult because they are very strong. So the DNA polymerase very difficult to get access to the DNA to start transcription, translation, and get the product. And that's why we think that, probably by losing the tight interaction between oligopeptide and the DNA, by adding dope, a natural lipid, it will help the transfection agent to release the DNA. And yes, we got it. Even though the particle size, if we add dope, is increased significantly, say from 100 to 500, but the GFP expression qualitatively higher compared to the oligopeptide itself, even comparable to lipofectamine. And the second question regarding the conclusion that the oligopeptide-based liposome mediate GSP expression comparable to lipofectamine. I know this is very sensitive. When I discuss with international speakers, He said that even though lipofectamine is toxic, and we try many times, and yes, it's toxic, and the particle size is bigger, sometimes 500, 400, or even bigger than that. But the facilities and the expression very, very good. How confident we are that the transfection agent that we develop comparable to lipofectamine. As I suggest in the future work, the main challenge of liposome preparation is stability. So I have to mention honestly that probably the liposome that we prepare, when we evaluate later on, say after a year or more than that, the efficiency may be less than before. And I tried, yes, it is quite less. Probably because the component of the liposome, which is in this case, I mean, in our transfection agent, is coming from peptide. Meanwhile, lipofectamine actually composed of those parts, and two is so different component, and that's why maybe the stability of lipofectamine much better than the peptide-based transfection agent. That's the challenge. Is it enough?
Okay, thank you, Mr. Tarwadi. I will continue for next questions from Dr. Trisuciati. Please, Dr. Trisuciati.
Thank you, Professor Daryono, and congratulations for Pak Tarwadi for your achievement and your nice presentation. And I would like to give like a discussion about 3 topics. Firstly, I would like to ask about how you overcome the variety of the liposome size. As you mentioned, that liposome size could be can be high and high. Could you please share with us what your experience to overcome this? And the second question, as you mentioned that you use liposome and nicely shown the transfection of the DNA and the expression of the DNA. And the problem maybe still, yeah, as you mentioned that the size of the liposome. Is there possibility to prepare a core cell delivery system where we put DNA in the core and we put the targeting agent on the surface of the delivery? Okay.
Excuse me, Bu Cici, could you please repeat the second question, please?
If you pack the DNA complex within the liposome, you have a problem like the size of the liposome. How about we make a single layer, like you use lecithin with twin maybe, that makes single layer, and we put the DNA in the core and the targeting agent on the cell as the coating, like coating. Okay.
Okay. Firstly, regarding the variety of liposome particle size. At first, we think about twin, to be honest, twin 20. And we try to put just a little bit, very little amount, about 0.5% in the liposome formulation. But it's still cytotoxic to the cell. And even though the particle size very nice, 50 nanometer, 50 nanometer, and stable over the time. 10 days. I observed for 10 days. The particle size we analyze using an analyzer, and yes, it's very, very nice. And it's also confirmed with the TEM data that the particle size so nicely, small enough, compact, and stable. But then cytotoxicity, and that's why I propose how to make the liposome stable, non-toxic, probably by choosing other polysorbates and also by optimizing the concentration have to be less than 0.5. That's what comes in my mind. And secondly, regarding how to pack the DNA in a liposome. Bu Cici and ladies and gentlemen, for my understanding, when the DNA complex by the liposome, DNA or say we can say a drug target, the drug itself or genetic material, almost always being packed inside the liposome itself. So the lipid will cover the DNA. Firstly, DNA will be compact by the main transfection agent, peptide, and then will be covered by the lipid. In this case, we use a natural lipid of dope, and that's why the presence of dope is making the complex less toxic to the cell, and then they will make a granule to penetrate the cell membrane. So that's my understanding. So almost every liposome-based transfection agent, they will cover the DNA or as the core of the liposome, and then after that they will carry to inside the cell. But as I mentioned, the main challenge in preparing liposome is stability. And also, I mean, when we compare to lipofectamine again, it's because it's different component, DOSPA and peptide. Peptide, probably if you do a first thawing, it will reduce the stability. And that's why after 2 or 3 years later, the stability of our liposome, actually degraded. So we have to think about it. Thanks.
Okay, thank you, Mr. Tarwadi. Next, I would like to invite promoters teams. First, Dr. Rahmana Imran, please.
Thank you, Mr. Chairman. Mr. Tarwadi, I would like to express also my congratulations for your achievement so that we can meet in the meeting for defense of your dissertation. Even though I have also 2 questions for you. The first one is that in your research, you develop a transfecting agent, yes? And if we see from the view of pharmaceutical science in general, it seems that your transfecting agent somewhat different mechanism, as the usual active pharmaceutical agent or excipient. Your opinion, your transfecting agent can be considered as active pharmaceutical ingredient or just general excipient? That's the first question. The second question is, if I understand correctly, in your experiments to show the transfection efficiency, you deliver the genetic material that produce the enzyme luciferase, protein luciferase, and it seems that it works well, that your transfecting agent can effectively enhance the production of luciferase. Can it be extended also for other genetic materials? Because your experiment to show the effectivity of this transfection process is limited. Yeah. This is the last question. Maybe it is about the modulation of the production of luciferase. By adding the chloroquine, you can show that can increase also the production of luciferase. So it seems that it works well also as modulation. That chloroquine can modulate the production of luciferase. However, in your dissertation, there is no further explanation about the possibility of mechanism of that modulation. Maybe you can show, explain us in more detail the possibility of that mechanism. So because other substances like the antibiotics, on the contrary, can reduce the production of luciferase, but in the case of chloroquine, increase. So thank you.
Okay,
So
thanks, Dr. Empran. So firstly, regarding the transfection agent, whether it's regarded as active ingredient or as an excipient. In my understanding, since the transfection agent means a factor, so it's not active ingredient. It's a delivery agent. So it's excipient. So it's help the drug, in this case mean genetic material, to get the active site, to get the proper direction. In here mean get into the nucleus. So transfection agent, in my understanding, is not active ingredient, but excipient, because it's actually only helping the DNA to go to the nucleus, which is facing so many barriers, intracellular barriers. And secondly, regarding the genetic material, in this case, we use a luciferase encoding gene as well as GFP encoding genes. So luciferase used for quantitative analysis because we can quantitate exactly, but GFP, green fluorescent protein encoding gene, is only to qualitatively that our transfection agent or factor facilitate gene expression. So basically, we can change the genetic material, whatever it is. And the main advantage of using non-viral transfection agent, such as that we developing, we can actually compact the big size of the gene that we would like to transfer to the cell. So we might use another genetic material that coding or encoding other protein, and then using our transfection agent. So using luciferase or GFP encoding gene in here actually just for the models to quantitate, to measure the quantitatively or qualitatively. And the third question regarding the modulation of transfection by chloroquine. Yes, actually chloroquine, but we have to optimize first, yeah, because chloroquine also having a cytotoxic effect to the cell. So before we choose the exact concentration, we have to optimize which concentration that okay for the cell. In this case, we try to use three kinds of cell: the HeLa cell, HeLa cell, COS7, and 290 cell. And the concentration needed to every cell is different. And how the mechanism chloroquine modulate or enhance the transfection efficiency. Actually, chloroquine involved in endosome escaping mechanism. So that's why even though polylysine condense DNA effectively, but not mediate DNA very low. When you add chloroquine in appropriate concentration, the polylysine will also mediate the transfection because it involved in endosome escaping mechanism. Because chloroquine is weak base, and then inside the endosome, it will attract the water and others, make it endosome larger and bigger, and then bursting. Endosome bursting and DNA which inside the endosome, because transporting DNA inside the cell always through the vesicle, such as endosome, and then DNA will free to continue the transport into the cell nucleus. That's what's my understanding, Dr. Rahmana Emba. Thanks.
Thank you, Dr. Tarwadi. Mr. Tarwadi. Next, I would like to invite Professor Heni Rahmawati to deliver your comment or question. Please.
Thank you, Mr. Chairman. So before I address my question and ask your opinion, I would like to congratulate Mr. Tarwadi for successful in completing a PhD project. I have two remarks actually, which you can address this, your opinion about this remark. So the first one regarding to the project, that your project was dealing with transfection efficiency enhancement by modulating the surface charge of the nanocarrier, the lipid-based nanocarrier, and also using transfection agent. So you mentioned that you are successful, to improve the transfection efficiency, by modulating the surface charge, and using the transfection agent. What actually the final goal of your project? What is the clinical implication of doing this kind of research? What kind of disease you would like to treat with this system? That's one, the first one. And the second one, in your conclusion, congratulations that you got a better system compared to the golden standard, lipofectamine, in terms of safety. So your construct is less toxic, compared to the golden standard commercially available in the market. But this study is based on in vitro study. So how you convince us this safety, when you want to bring this product to the application? Okay, please, Pak Tarwadi.
Okay, thanks, Prof. Heni. So, first question regarding the final goal of the transfection agent that we developed. Actually, for the short term, we would like to get the transfection agent which is safe and effective. That's the main goal. So many transfection agents, they may safe but not efficient. Not efficient in facilitating gene expression, or vice versa. They may effective in facilitating or mediating gene expression, but not safe for the cell itself. So this is the main goal of the project, to get the transfection agent which is safe and effective. the clinical implication, if we would like, say, deliver the gene, say, for encoding certain a certain protein, such as for the diabetes mellitus, yeah, we can condense or complex the DNA encoding certain gene, yeah, then we have to make it in animal model first before we going to human actually. So this is very long way to go actually, because we have to prove that in vitro experiment our transfection agent is effective and efficient, and then go to in vivo in animal model, and after that to the clinical stage. So Prof. Henny, this is very early actually. What kind of disease in gene therapy actually, Prof. Henny and ladies and gentlemen, there are so many diseases that can be cured by a gene therapy approach, whether cancers, whether infectious disease, or even the genetic disorders. So once we know exactly the mechanism of the disease and know exactly the kind of gene that we would like to deliver to the patient, then we have to compact or condense that of gene with the transfection agent, which is safe and efficient. That's the dream of yeah, long way to go. Secondly, regarding the toxicity, book, can you please repeat again the second question?
So you compare your successful product with the golden standard lipofectamine in terms of toxicity, and you concluded that your product is less toxic, yeah, compared to the lipofectamine. But this based on in vitro study.
Oh yeah.
So how you convince us that this safe product also will be safe when you want to bring to the clinic?
Okay, thanks a lot, Prof. Henny. Yeah, actually, we did several experiments using different kind of cell lines, so still in the in vitro, and the data telling us that the degree of cytotoxicity of our peptide or oligopeptide is less compared to the lipofectamine. Of course, we have to move to other cells, yeah, such as stem cell or non-dividing cell, and as well as like zebrafish, a small animal model. And then we are very convinced that our transfection agent is much better than others. But in this stage, when we use the cell line that we reported in our research publication, clearly observe that our transfection agent less toxic in vitro compared to the control. Yeah. In here, we compare to polylysine and lipofectamine. But of course, to make sure that is really better, we have to move to other kind of cells, as well as stem cell, non-dividing cell, and then move to animal model for the next experiment. Thank you.
Okay, thank you, Mr. Tarwadi. Next, the last one, I would like to invite Professor Sukma to deliver your comment or question. Please, Professor Sukma.
Thank you, Mas Daryono. I would edit my first presentation about the publication, Mr. Tarwadi. We have 3 publications in international journal, and we have also 3 publications in national journal, and then we have also 6 publications in Seminar International. My question, first I would like to explain Mr. Tarwadi about the phenomena of complex molecule in our discussion about complex is their DNA and peptide. In general case, the particle size is more big to compare each molecule different. I mean,
Please more closer your microphones, Profesor Sukma. Mikrofonnya mohon lebih dekat.
Kedengeran ya. In phenomena of complex, in general, complex of 2 molecules different will have the particle size more big than each molecule. But here in your research, we can find the particle size of complex is not bigger than each molecule. Can you explain about this question?
Okay, thank you. Please, Mr. Tarwadi.
Kedengeran nggak?
I couldn't hear what from here.
Kedengeran.
I couldn't hear from
Your
here.
dissertation.
Okay, you can speak in bahasa Pak Sukma, Profesor Sukma, you can speak in bahasa, and mikrofonnya mohon bisa lebih dekat.
Jadi maksud saya adalah, kedengaran nggak?
Belum Pak, maaf Pak, saya mungkin perlu pakai headset Pak.
Complex is constitute
Ternyata ketinggalan. Ya Pak.
Oke, please.
Silakan Pak.
The phenomena of complex in general as the particle size more or same the combination of size each molecule. But in your dissertation, you explain that the particle size of the complex is not more than each molecule. Apa dengeran ya?
Oh, oke. Ya, baik. Jadi
Saya pakai bahasa
Okay,
Indonesia.
you can hear
yeah.
the questions, Mr. Tarwadi.
Can I
Okay,
speak bahasa
yeah.
Indonesia?
The first one is about the phenomena, the interactions, yeah. And the second one is about the complex stability, yeah, regarding to the size of the particle, right?
Okay.
Yeah.
So, okay, I'll try to respond from the second one. The complex stability is actually based on many factors, but in this case, in our case, we follow the particle size as well as the zeta potential value.
Right.
So if the zeta potential value, mean the charges of the particle, is getting high or positively charged, the particle size tend to be compact and stable. And that's why our oligopeptide, which is composed of 15 positively charged of amino acid, is more stable than the one with the short lipopeptide, which only composed of 2 amino acids of lysine, which only means 2 positive. So in many experiments, we found that whenever you have more positively charged of amino acid, you will end up with the stable and compact particle size. And regarding the first question of Diana, could you please repeat the first question?
Regarding the general interactions.
Okay, yes.
Yeah.
Okay. So the general interaction in this case between the DNA with our translation agent is actually ionic interaction, so not covalent interaction. And that's why we try to put like lysine, because lysine is positively charged. Yeah. And also arginine, because arginine positively charged. And the number of the positively charged of amino acid, whether lysine or arginine, make it the compact of the DNA translation agent is getting smaller. And we can see it in dynamic light, dynamic scattering light, yeah, or in TEM image analysis. So the interaction between DNA and the translation agent is actually based on ionic. And whenever you have the natural amino acids like histidine, it tends to be bigger. Even if you have 4 or 5, I can't measure the particle size because the complex sediment tend to aggregate or tend to sediment because it's not enough for ionic interaction. Demikian, Prof.
Okay, thank you.
Okay, thank you, Mr. Tarwadi. The last one, I would like to invite Dr. Jalal Jayasari. Do you have comments or questions to be delivered to promovendus, please?
No, it's all good. And I have and just congratulate Tarwadi for what he has done and all the best to him.
Thank you, Jalal. Thanks.
Okay, thank you, Dr. Jalal Jayasari.
Thank you very much.
Yeah. Okay, ladies and gentlemen, we just finished the first session of the dissertation defense. And then I will ask your patient to give opportunity to the graduate school commission to conduct evaluation meetings. Then I will suspend the sessions for about 30 minutes.
I have to leave, all right?